You? No, I'm just thinking.
How much memory do I have? I should have a lot.
No, I have enough.
What? No, it tells you how much minutes of recording there is.
Doesn't matter. I've got this as backup.
The shower. The shower.
Might as well take some videos of me.
No board. Have you done this?
What do you mean, have I done it? I've gone to the notes, I'm not going to the example. It's not, I don't see it. Yeah. Pass it. This is the example you need to do.
I was doing the one about vibration.
Yeah?
You already seen the example of this one? Yeah. The vibration book like this. It's effectively the same thing. That's the same. No, I know you're true.
Yeah, I don't understand like which bits like I don't. There's not that much by actually. Like it's just this stuff here that you need to do extra, isn't it?
Alright.
Like this stuff's all columns, right?
Yeah.
This is just like just statics and stuff. I think maybe this is the only bit. Yeah, I didn't really get all this sigma mz and sigma myd.
I can't find the formula for them either. I don't know where they are.
Huh?
That's the same as MYD.
This is my of this is my of w, right? This is mz over wz. So all you swap the b and the h around for the z. That's by actual bending. The only thing you need to notice is you just make sure you just check the effective length in both directions. That could change as well, and that's effectively by accident. That's why it's only like one paragraph. Turn the thing over. No, turn the page the other way.
But now it's like the whole somebody must have some question.
No.
I know exactly what you mean about that graph. Sophisticated.
Okay, just while we're waiting for to see if we can get some more chairs.
This is the whole bag of bending.
With such a big group, it's sort of difficult to be absolutely sure what's the best to do. But what would you hope
A bit of
that I
masonry.
would do?
Masonry.
But what well, we'll try and get all the ideas, so don't feel they're exclusive. But somebody says masonry, for instance. What about masonry? There's about 10 lectures there, so do you want me to give the lectures again?
In the part of ordinary chains.
Sorry?
The part of ordinary chains, where possibly retains from the group.
Any good? Let's have lots of ideas, and then we can try and distill them.
I drew E27, which is big enough, but if you have your own board marker, because it's a whiteboard now.
Yeah, no, I haven't got any of those.
Could we find any of those anyway?
Let's get at the front.
How many people are stuck out here? 10.
How many pieces of it?
Then where are you going to be at the back? Wait, the tables are going to be 10.
I'm I'm packing up already.
Okay, so we've got masonry. What else about
I
masonry?
came early for a reason.
I'll have to come and see what you mean by return. People waiting downstairs when I came in. People just sitting downstairs like, okay, we get a seat.
We were hit in the wrong room.
It's not problems you're interested in so much. I knew it was there. Basic
Problems.
eccentricity, really.
Problems.
Yeah, it's problems. Okay, let's go on. Anything else then? Anything else? You know
The part about so this is in the case of composite beam. If you could go through, you know how you get on top construction, how you get those equations and the signs as well.
I know. It is clever. I know.
Yeah, okay. So,
It gets too specific, innit?
You got that. None ask what he wants at that rate, but whether he doesn't understand, it's
Cells.
I think it's going to be quite tricky to do.
Please don't.
It's fine. It's
You don't want to sit on the corner, do you?
no, it's fine. It's fine. It's fine.
It's fine for you.
Right,
How's it gonna affect you?
there are the notes.
You can see
There's
it.
the screen. Can you do it?
Do you want to swap places?
Can you see?
I can see it.
I tried to attempt a few exam pastoral questions on masonry.
I was going to see it. Nice.
I was
It's angles.
many.
It's the perfect place.
So many different things there. It's going to be difficult to satisfy.
I mean,
Every angle.
mainly on the topic of masonry, if you go through sort of a question that has all the elements, I think that might help quite a bit.
I can explain this shape now.
Grab that chair.
Do you think there'd be any merit in doing
Sit down on
two
the other.
bits?
He's sit down on the easy.
I think you can explain this bit.
I'll
I'll explain it to
half
him.
people here.
He has to learn.
What?
Oh, this bit here. The
It's so
reason,
simple.
the reason is like,
Who wants to do masonry?
That's a good idea.
Who wants to do composites?
Okay, so masonry wins probably on that. I'm going to be around. This isn't exclusively. I've been here all week. And quite a number of people have been to see me. Yeah. Okay, what about the structural analysis then? Is there anything on that anybody wants? Okay, because there's certainly not much on structural analysis.
Two guys back there.
Just a couple, but
You know about stiffness. A lot of people want to know about stiffness.
okay, but the design seems to be the more
Mason.
Yeah.
the more relevant, doesn't it?
We'll get
Right, what could I think of?
Wave. There are two sections, right? Isn't it that one from 10, 9, 10 to
No,
10?
but it's my main. Yeah. This is because so this is like a composite action. It's only these two.
Yeah.
And then it's obviously only so it's only the IS term. It's only the shots.
Yeah.
But in this bit here, in the steel itself, because it
If there were
still
some more
takes
chairs, some
the
people could
steel's
come
taking all the
sit
long
in
time.
there.
So and then because of the diagram thing,
They might be in the other rooms to tell them to get.
from this. Where's the thing then? Yeah, see it. And it's from one of these diagram things, whatever, yeah. Because it's in the middle there.
I just wonder whether we need another session. Are you okay at the back there?
Wherever the control is. It's acting.
Do you want me
The
to?
HS one,
Yeah, the space
in the opposite direction to the HS2 bit.
We could do it again.
Because there's a moment
So,
around
you know,
here in the library, yeah.
if some people can't sort of fit in or comfortably fit in, we can repeat this
along with the composite.
one day next week if you want.
The HS one bit goes that way, and the ML times HS2
That makes
goes the
sense.
other way.
Or should we just have a go?
It's a bit of a hard schedule, but I think we could fit in.
Okay.
We can squeeze more people.
Yeah.
Rich, do you want to come in front? There's few spaces at the front.
Just sit on the floor along the front.
There's some people lying on the desks.
Just what?
We'll choose which people.
Go back
Oh,
home.
okay.
Go back home.
We can do that.
I just want to go back now. I don't want to.
And everyone move forward.
I've got back a couple of years.
Is that sus?
Yeah.
Got my
Sus? No, no, I was like, yeah, I'm moving forward. So I don't understand how that works. So only the front row moves in. Your fault, I haven't told you. Your fault. No one's like, I'm dead. I used this guy. I thought, okay, he was on my floor, so I thought I couldn't. I was referring you. I slept at 4. Yeah, in my. He was sleeping across my floor. He was like, yeah, so I was like, and you could have noticed, but because I was referring you to help you out. figure out in the way to know. No, breaking out. I forgot what that. I think it was that whether we need to come back home or not. This was about vibration. No, it was about vibration book is what I said. Oh, I think meant about oscillation. I said about
But this room was not designed for 120 people. Architects had no idea.
it reminded me about
We'll exceed the load.
I think we have a candidate.
Well, you were cooking it after talking. Oh no! Yeah, I'm thinking.
Huh? Never mind. Far behind.
Oh, where did you get this one from?
Oh, well, this is pointless.
Basically, huh?
Well, this is
You still have to go. It's people take a rotation into a zero. The zero means angle, so it'll always be zero. It's just same as it's basically sigma CD, and that just basically means
Sigma express, yeah.
sigma
so,
stress.
no, this is from the notes.
Right about area.
Yeah.
Right. Okay, we'll have a go anyway. See how we get on.
They take them up.
Somebody just mentioned shear in masonry there, a couple of people did, so we'll perhaps kick off with that. This is just from the notes, what I've got here. But perhaps with that I can just explain to you what it is. And then there is an exam question which we could have a look at, even if we don't write the whole thing out. We can go through how you deal with it. Okay, so basically masonry walls are pretty good for carrying shear loads. Very often they're put within steel frames and concrete frame structures purely just to do that. They mightn't carry much vertical load, but they can carry that. So if we have an outline of a building like that, and some lateral load coming on it here, okay, so that could probably in practice be due to wind, then that load will be resisted by the lines of these walls there. If the load comes on the side of the building, the walls stop or resist that load. So it's almost as if we had, if you like, our building, the wall across the building is there, the load, the wind load is blowing on here, and you've got this to carry it. So imagine a distributed load up here, or a point load at the top. It's going to try and bend the wall like that. Now the shear is carried along the horizontal joints in the wall. Shear strength of masonry is very high. To determine the shear resistance, you just need the area of the wall and the shear strength of the masonry. So that isn't really very difficult, and I guess that wouldn't cause most of you any difficulties. Where difficulties often come about is when you've got this wall stuck up like that, you've got a load on there, the shear bit is easy, but there's also a bending bit like that. And how do we deal with that bending? So, first thing to do is find out in the series of walls how much of this load W is carried by each of them. A case like that, what some people would do in practice would simply say they'd work out the load on that elevation, the load on that elevation, and take a half of it there, and do the same for each of them. And if you do that in practice, and everything works, it's fine, it's conservative. But in fact, when you put a load onto a series of structures that are linked together, the way in which that load is distributed in proportion to its stiffness, or the stiffness of the resisting walls. So this load here is shared into the 5 walls I've got up there in proportion to their bending stiffness. Bending stiffness is EI over L. So if all the walls are the same height, you can forget the L, and it's the EI values that will count. So the total load is shared between the walls in terms of the EI value of the wall you're looking at, divided by the sum of all the EIs in there. Now, I've got these side by side. The same would be true if they were in line, one behind each other. The load is carried in proportion to the stiffness. So that you need to know and understand.
Will we be given the E values, or will we have to find them from the table?
No, in terms of an examination, any values you need, we'll give you. We'll look at a problem in a minute. Very often, you're just asked to get an answer in terms of, say, EI. So that's the principle that lies behind distributing the loads. Again, this was directly in the notes, and it's just an example that I had up there, where we looked at 3 walls like that. They've actually got different thicknesses. That was a solid wall, and those were 2 cavity walls at the end. Cavity wall, 1 leaf of masonry, gap, and another leaf of masonry. But since the gap runs that way, as far as working out the stiffness is concerned, the EI value, you can just simply ignore that. So the I value, and this is where people often go wrong, if we want to calculate the I value, the thickness of that wall, I think, was 225, and the length of it was 5840. So the wall looked like something like that. So this central wall, 5840, and the thickness 225. This is in plan, all that, and effectively we're going to be applying a load like that. So if I just come back to my folder here, that wall there looks like that, and we're trying to find out how much of this 150 kilonewtons goes into that, first of all, and then what it will do to it. So we need the EI value for this wall. E, I think all the E's were the same, so we need EI to the wall in question over the sum of the EIs. E is fairly straightforward. Where people sometimes get mixed up is I. And what I is B d cubed upon 12. So you need a B and you need a D. Now this relates to the plane of bending. So what we're doing is trying to bend that wall like that. So the axis of bending is through the centre of the wall. So in this case, the B is 225 and the D is 5840. So that would be the I value you take. Sometimes in problems people will look at that and think, oh, that is B, that is D. You just got to think about the way in which the bending acts. If that wall was orientated the other way, in other words, if we had it like that, it wouldn't make a very sensible shear wall then. But in that case, the B, for a load coming this way, that would be the B and that would be the D. But the value's small, so it just wouldn't be sensible. So we have to calculate EI over L for that wall, and then divided by the EI over L for that one, plus that one, plus that one. And that'll tell us how much of the 150 goes in there, and how much goes into those side walls there. So that's usually the first bit of one of these problems, how you distribute the load. Yeah.
You know, because all the walls have got the same dimension, does that not mean that
They've got different thicknesses. They've got the same longitudinal dimension. But that wall is 225 thick. This is a 280 cavity wall. So the other wall would be... Just think. We've got that there. So we've got one. So that overall is 280, and it's made up of 2 walls there that are each 2.5, which is the thickness, the width of a standard brick wall. So for a cavity wall like that, if we want to calculate its EI, it's E times B d cubed upon 12. Remember, we're bending it about this line here, so the B is the width of the material we've got in that direction there. So it'd be 102.5 plus 102.5 B times the depth is still 5840 over 12. So the fact it's overall 280, you don't use 280 in there, it ends up as, what did I say? Yeah, 205. So that would be 205. Again, sometimes in a problem like this, people say, oh, the overall wall's 280 thick, and they'll use 280 in there, which would be wrong. So you've just got to think about what it is that we've got. Is that okay? Yeah.
If you had two separate walls of different materials, obviously two E values, you have to then equate them.
You would have to use the E then. Yeah. So supposing we had one, let's say that was block, and that was brick. Okay, then the EI for that wall would be EI block and we'd have to add to that EI brick. So you do them separately. So if we had a different E value there and a different E value there, or different thicknesses for that matter, you've got to combine them in that way. It's easy in this sense because it's all additive. If you're looking at bending the other way, of course, it'd be much more difficult. So that's a good idea for an exam question. That change the thickness. I suppose that's a hint that I haven't done it this time. Okay,
Yeah.
so is that okay? That's just an area where people do seem to get stuck on these problems. So, is there anything else about how we distribute the load to the walls that? Yeah.
Why do you ignore the horizontal walls?
Well, because if you're bending that way, okay, predominantly the stiffness is in there. Now, actually, if you read through the whole of this problem, I also reworked it, taking account of the horizontal walls in there. So initially we just took the plain wall, and then I worked it out again for an I section. And that was down under there. Now, you could do either. Clearly the simple one is just to take the line of the walls. And if that works, usually in practice that's what people would do. But you certainly could take those, and I just wasn't going to complicate it now, but if anybody's interested, just down under there, you can see you get a different distribution of load in the walls. So if we just take the walls themselves, you get 48 kilonewtons there, 48 there, and in the middle, 53. If you take the I sections into account, you get 36, 36, and 77. Because now you've got a stiffer entity here, so it pulls more of the load to it. Okay. So that's the first thing one has to do. And then it's a question what you do with that information. As far as the shear itself is concerned, I've probably got to get a better picture in here. So there's two things then. Those walls will have to carry bending and they'll have to carry direct shear. The direct shear bit is sort of fairly straightforward. Again, this is just straight from the notes. if you've got a shear force coming on there, and let's assume we've got some vertical load. There's no vertical load. Well, there's always got to be some vertical load because you've just got the self-weight. But sometimes you might have a floor sitting on this wall, and that would put an axial load into it. Now, when we apply a horizontal force across there, and that could be a distributed load up there, it would give you the same turning effect like that. Then what happens within the masonry? Well, one thing, this shear force here has to be resisted along these planes here. And there it's purely the shear strength of the masonry times the area of the masonry that's in compression. Okay. So it's just shear strength. You've got that sort of thing happening. You have the shear strength of the masonry, the area over which it acts, times the shear strength, gives you the shear resistance. But if you have the load coming on like this, it's causing a turning effect for that wall. In other words, a bending effect. So you're going to get higher stresses here, vertical stresses, than you will there. What we say for masonry, we ignore the tensile strength of masonry. So if we do that, the stress block we need to resist the turning moment will look something like that. Now, think about that, how you might work that out. So if we've got our wall here, something like that, at a base there, we've got a horizontal force S there, with a vertical load P in the middle like that, then that wall is subjected to a vertical load that's equal to P and an overturning moment. And if H is the height of the wall, the overturning moment is just S times H. So we call that M. So it's like for saying we've got a P and an M. Now we start off with the mason, we looked at the thickness of the wall and we looked at load eccentric to that. Here now we've got the length of the wall, but it's the same sort of effect. But now we're acting over that area rather than over the cross section, which would be in there like that. So we've got moment is S times H, which we could call that equal to M. Now once you've got a P and an M, you can think of that as effectively shifting this load over that way by an eccentricity E, such that M is equal to P times E. So the eccentricity is equal to M over P. So we can replace this situation by just putting the load there, where this distance is E, the eccentricity. Now if we're going to balance that with a rectangular stress block, then we're going to have something that looks like that, where the center of this stress block has got to be equal to P and it's got to line up with that there. So if we can calculate E, which is M over P, M is S times H, S is what we got from what we did there before. We can now look at the stresses in the wall that resist this combined shear and vertical load. So if you know the length of the wall, let's assume the wall has a length L, this distance in there will be what?
L minus E over 2.
Sorry?
L minus E over 2.
L?
L minus E over 2.
No?
L over 2 minus E.
L over 2 minus E. Okay. So that's what that is. So the total width in there will be 2 times L over 2 minus E. So